on all the equations after e, like e to the
It's minus t.
Okay.
Yeah, it's a function of time, so the time has to be in there somewhere. Any other questions? Okay, so let's do the standard charging circuit, which is a little bit more tricky. Many ways very similar, but has some important differences. So this is your standard charging circuit. It looks like this. So I know in a certain sense it's kind of backwards because I did the discharging first. You might say, how did that get discharged in the first place? Well, I did that one first because it was easier, but the way that you get the charge onto a capacitor is by charging it in the first place. You can discharge it later if you want to get the stored energy off of it, but we got to get it on there in the first place. This is how we do it. So we have an empty capacitor. So let's go ahead and write down our variables again. Let's do Q, VC, VR, I, PE, and P. So we'll go through the same progression. We'll just kind of conceptually figure out what happens, and then we'll put some mathematical form to it. Right? So this capacitor is going to be empty at first. Blank slate. It has no charge on it. It therefore has no voltage drop. Remember, these two are always tied together. As goes Q, so goes VC. So we don't have any charge on it yet, so there's no voltage drop across it yet either. So let's take a look at what happens in terms of getting charge on there. Well, what's going to happen here is that charge is going to flow on here from the battery, and the resistor being put in the path somewhere means that it can't just go on there instantaneously. The resistor can be either before or after. Remember, this is one of those things we have to remember, that if the resistor is after, it's not like it gets surprised. Okay? It's always charge carriers moving through the entire system at once. So it doesn't matter if the resistor is before or after. I just drew it before because I had to pick one. Let's go ahead and mark off in general. There are going to be, in general, 3 different equipotential regions in this system. A, B, and C. And here I'm going to make sure this is lowercase c and do my best to draw it in green so you don't mix up the labeling of the equipotential region with the capacitance. This is pretty much the same deal as any series circuit, right? Anytime we had 2 resistors in series connected to a battery, it separated the equipotentials into a high, middle, and low step, right? So if we had to characterize, in general, what's going on here, we might write something like this. This is VR, this is VC, and we're separating it into a high, middle, and low step. So that's kind of what we can expect in general. However, at the beginning, we already had said that if you don't have any, or I guess let me start with A and C, of course. These are separated by the battery, and the battery provides a fixed voltage difference between regions A and C, right? So this here is fixed from here to here. But we had already said that there is no charge on the capacitor yet. And if there is no charge across the capacitor yet, we can safely say that region B and C are not different. This, whatever this is, going from here to here, this is the same. So at first, if is no voltage difference across the capacitor, then B is actually not any different from C. So I'm going to actually go ahead and take this, which is the general situation, and remember that it evolves with time. And I'm going to go ahead and sketch out what it looks like initially. So initially, I'll put over here. I'll put final over here. And this is actually going to represent the general case just sometime during charging. So at first, here's what you have. We said that B is essentially the same as C, so we have to conclude that if you have no voltage drop across the capacitor, it must be all across the resistor. Okay? So we know that the sum of these two has to add up to the battery voltage. But if the capacitor has no charge on it yet and has no voltage drop across it, the resistor has to take it all. So we can safely say that the resistor initially has a voltage drop of all of it. Okay. And if the drop from A to B is actually the entire voltage of the battery, there is definitely going to be a large current because there's a large voltage drop from A to B. In fact, remember that these two always go together. Ohm's law dictates that they have to stick together. So therefore, if you have a large voltage drop across the resistor, you're going to have a large current. So there's a tremendous rush of current. The initial current, in fact, is determined by the battery voltage. That's the only thing holding back the current from being infinity and flowing immediately is the fact that there's a resistor in the way. All right. And then, I guess to finish off the initial column, how much energy do we have stored at the capacitor at the beginning? 0, because we don't have any charge yet. PE equals 1/2 Q squared over C. So you don't have any charge on it yet, so there's no potential energy. Are we going to have power dissipated in the resistor? Remember, that goes as the current. So if you have a surge of current through the resistor, you're going to have a lot of power. In fact, the initial amount of power is going to be tremendous. It's going to be the largest it ever is. You can plug in the current if you want, and you get that. So at first, basically the circuit functions as if the capacitor weren't even there. Okay? The resistor is experiencing the full voltage drop of the battery, and the reason why is because the capacitor has not yet had a chance to get any charge, so it does not take any of the voltage drop yet. Now that will change. So let's take a look at what happens. Obviously, if current flows through the resistor, where does it go? It accumulates on the capacitor, right? And as the capacitor gets more charge, it gets more voltage drop. So what happens is that this will increase over time, and this will decrease over time because they have to add up to the same amount. So you can kind of think of it as B. Initially, equipotential region B is essentially no different than C, but then it starts to creep up. And in the process during the charging, it's creeping up. So again, as the capacitor receives more charge, it takes more of the voltage drop, and it crowds out the resistor. So this is increasing while this is decreasing. Okay? So again, think of it as a time evolution. These two things are in series, but how much they each take of the voltage drop is evolving with time. As the capacitor gets more charge, it takes more of the voltage drop, and then it's crowding out the resistor. the resistor takes less voltage drop. And eventually, what happens? Well, it looks like this. The capacitor has finished crowding out the resistor entirely. The equipotential regions A and C, which are directly connected across the battery, they're still there. Where is B? It's at the top. It's finished climbing all the way to the top. Okay? So B has changed its alignment. It was joined up with C, but now it's joined up with A. Equipotential region B is now the same as A. Okay? So, if A and B are exactly the same voltage, does current want to flow from A to B? Why would it? It has no reason to. Now B is the exact same voltage as A, so charge doesn't flow for free. It does it for an energy reward. So the voltage across the resistor goes to 0, and of course that means the current goes to 0. Of course those two always stick together, right? So once there is no longer any reason, no reward for going across the resistor, then nothing will actually flow. What's happened? The voltage across the capacitor has grown to that of the charging battery. So I want to point out here that as the voltage across the resistor, across the capacitor increases, the one across the resistor decreases. So now they go inversely. They don't go together. They went together over here because these were literally the same voltage drop. These two regions across the capacitor or resistor. But now there are three different equipotential regions, A, B, and C. And so the voltage drop from here to here can generally be different from here to here, right? The voltage drop from A to B and B to C can be different. The only thing that they have to constrain to is adding to this, right? They're in series. If you want to do the loop rule, you could do around this gain, drop, drop. Or you could just say, oh, I know these two things have to add up. This is fixed by the battery, but as the capacitor charges, this takes more and this gets less. Okay? So they're in series, so they don't generally have to have the same voltage drop, and in general they don't. And in this case, one increases at the other's expense. So what we just said right here, one increasing, one decreasing, if you want, we can write it here. So initially, this is all of it, and this is none of it. And at the end, there's none of it, and this is all of it. So they traded, right? And somewhere in the middle of charging, they'll both have some. So the general case is that the capacitor already has some charge, so it already has some voltage drop. But there's still some voltage drop across the resistor as well, which means that charge will continue to flow and charge this. At the end here, when the current shuts off, well, that's the delivery mechanism of getting stuff to the capacitor. So whatever charge we're at here is the end of the line. I'll call it Q full. Once the current shuts off, because there's no reason anymore for it to flow, then that's what cuts off the delivery, and whatever charge the capacitor has then, that's what it's going to get. Does that make sense? And then, the potential energy that it's storing at this moment is the most it can be. So this would be 1/2 Q full squared over C. So that would be the amount of energy stored. And what happens to the power dissipated through the resistor? 0, right? The resistor is no longer sweating out any energy because there's no charge coursing through it anymore. There's no current flowing through it. So now we've stored up as much as we're going to store. I want to point out that during the charging process, you do waste energy. There's some energy being sweated out through the resistor that doesn't end up on the capacitor. But at the end, once you're done, the amount of energy that made it to the capacitor is going to be there stored waiting for you. And of course, you're not wasting any more energy through the resistor because you're done charging through the resistor. Does that make sense? Sort of. All right. So that's what happens to all the stuff. I want to point out, if you're looking for a common theme, the things that are associated with the capacitor are growing, right? You have more charge, more voltage drop, more energy, and then everything that goes to 0 is related to the resistor, right? Because once the resistor is basically not involved at all once you're done. The resistor was involved during the charging process, but after that, you basically just have energy sitting on a capacitor ready to use. So notice again that the things involved with the capacitor are growing, and all the things associated with the resistor are shrinking. Question?
So the only reason we're using a resistor is so that the current doesn't go crazy and overheat all the wires?
Yes, that's definitely one reason, because you could literally easily fry a wire. And the second reason is that you can't escape resistance even if you wanted to. It's kind of not possible. And the fact that these evolve with time is a feature, not a flaw. Because if you want to have any kind of circuit that involves some time, like the blinkers on your, when you're changing lanes, or any kind of circuit that involves time evolution, it uses a capacitor. It's a feature, not a flaw, right? As much as it's annoying that you have to deal with a time element, that's oftentimes you want that to be available in a circuit. So let's go ahead and do our best to write down the functions. So again, I'm going to give you the bare minimum, and then the rest you can get yourself. So here's the charge function, and here's the current function. You'll again find these on the equation sheet. You don't need to be able to derive them, just use them. And if you are looking for 4 functions on the equation sheet, because I gave you here a charge and a current function for each one, there's actually only 3, because if you notice, this current function is exactly the same. So all you have to do, there's 3 equations on the equation sheet. There's a charge function for each one, and then there's a common current function. So the current function is exactly the same as the discharge circuit. Same exact deal. There is again a time equals tau. That again represents the dropping 63% from your initial value and only having 37% left. And the tau is again determined exactly the same way. It's the capacitor you're charging times the resistance you're charging it through. So you'll only find one formula for tau as well on the equation sheet. It's the same exact thing, R times C. So the charge always goes to 0 in both circuits. Why is that? Well, eventually, there's nothing left to do over here because it's done discharging. Over here, there's nothing left to do because you're done charging, right? So regardless, your current has to eventually go to 0, right? So current goes to 0 at t equals infinity because you're done with whatever you're doing. So you're either done with the charging, or you're done with the discharging. That is why the current always goes to 0. And that current, by the way, is used in anything else that you would have, right? The current is tied to the voltage across the resistance. So that's going to go to 0, okay? So remember, we said everything associated with the resistor goes to 0. So the voltage across the resistor as a function of time will be the current as a function of time times the resistance. That looks like this. What is that quantity in parentheses again? The initial voltage, right? Which is what, by the way? Remember, all the voltage drop was across the resistor first because there was nothing yet to across the cap. So that's your voltage across the resistor function. And blah, blah, blah. You can also get, off that same current function, you can get your power function, okay? That's all pretty much the same stuff as before. But the interesting stuff is not the stuff that's associated with the resistor, which we said ran down to 0. So it ran down to 0 before. But we also have that we said that everything associated with the capacitor is increasing. The charge on it grows to Q full from being empty. The voltage drop eventually is all across that too. And then, of course, the potential energy as well. So let me do that real quick. Here's your function for the charge that was given. The voltage drop across the capacitor I can get from it. Remember, they're related by the capacitance. So that's going to look like this. What is this right here, by the way? Q full over C. Well, Q over C in general is the voltage, right? So what's the full Q over C? That's the final voltage, right? Which is what? Now it's the entire battery. So this we get looks like this. So that's the voltage drop across the capacitor. And I guess you can do the potential energy as well, right? So potential energy function will just be 1/2 the charge function squared over C. So I'm out of time. I didn't quite get a chance to look at this new equation that obviously looks a little bit different. It's got this 1 minus bit. So what I want to do is I'll start with this equation, and this equation. And I'll kind of explore their interrelationship at the beginning of next time. And so if you just refresh just a little bit on the charging circuit before that, then we can jump right in. Okay, so that's it for today.